Bismillahirrahmanirrahim. Today we are going to discuss generalized Hooke's law, or also called Hooke's law in triaxial state of stress. So let's first recap what's Hooke's law in uniaxial stress. So if this is a bar subjected to uniaxial tension, let's say, and you consider any element inside this object, then on this element we have stress only in one direction. So this is state of uniaxial stress. Now for this uniaxial state of stress, Hooke's law, it relates stress and strain in the same direction as the stress applied. So stress in this direction and strain in the same direction as the stress, as the direction of the stress are related by this equation, are often symbolically represented as sigma equal to E times epsilon, or epsilon times E, whatever you like. So we can rewrite this equation for strain in the same direction as the stress applied. So this can be written as strain in the same direction as the stress applied equal to stress applied divided by modulus of elasticity. Important thing to keep in mind is in uniaxial state of stress, Hooke's law relates stress and that strain which is in the same direction as the stress applied. Now let's recap another effect, Poisson effect. If you look at this object and you apply a stress in this direction, it will of course produce strain in the same direction as the stress, but will also produce strain in the other two perpendicular directions. So Poisson effect relates these two types of strains, the one that occurs along the direction of the stress and the other direction strain, and the perpendicular direction or lateral direction strain. So strain in the same direction as the stress applied is equal to stress divided by modulus of elasticity. This comes from Hooke's law for uniaxial state of stress. In order to determine strain in the same direction as the stress applied, we can apply the same Hooke's law in uniaxial state of stress over modulus of elasticity. But in order to determine strain in the perpendicular direction, in the direction perpendicular to the stress applied, which is this direction in this figure, and the other direction is this one, the strain in these two directions can be found by this expression, minus Poisson ratio times strain in the same direction as the stress applied. Now strain in the same direction as the stress applied, this term we can replace it by using this equation. So we can make some substitution and we can write this second equation as strain in the direction perpendicular to the stress applied is equal to minus Poisson ratio times stress over modulus of elasticity. We have just put the value of strain in the same direction as the stress applied from this equation. So third equation and this first equation, these two equations are enough to get strain in the same direction as the stress applied and to get the strain in the other direction, in the perpendicular direction, by this third equation. So this first and third equations, these are going to be the base of what we're going to discuss in the next slide. So Hooke's law in triaxial stress can be derived as, if you consider a triaxial state of stress, let's say sigma x, sigma y and sigma z, all three are acting on an element, and let's consider them to be tensile for this derivation. So we can break it down into three steps, considering sigma x separately, then sigma y separately, and then sigma z separately. So let's make a table and see what strains are produced when each one of these stresses are applied. So let's consider stress applied, and then we will consider for that stress applied what strains are produced in the three directions. So let's first consider sigma x. So when only sigma x is applied, these like this, then strain in the same direction as the stress applied would be equal to stress over modulus of elasticity, and strain in the other directions, perpendicular directions, would be minus Poisson ratio times stress over modulus of elasticity. So when if stress applied is in the x direction, sigma x, then strain in the same direction, strain in x direction, would be equal to simply stress or modulus of elasticity. So stress in this case is sigma x divided by E, modulus of elasticity. And strain in the other two directions, y and z directions, would be minus nu times sigma x over E. This nu is Poisson ratio. So what next, consider sigma y. When you consider sigma y only acting on the element like this, then strains in the same direction, as the stress applied, which would be strain in y direction this time, because now stress in the y direction, so strain in the y direction would be equal to sigma y over E. And in the other two directions, x and z, the strain would be given by this formula, minus Poisson ratio times stress over modulus of elasticity. There we go. And then lastly, if we consider sigma z, then strain in z direction would be equal to simply sigma z over E, and In the other two directions, we would be having minus nu times stress over modulus of elasticity. Now, let's summarize this in the next slide. This is the same table that we developed on the previous slide, and if we just sum up strain in x direction, if all three are acting simultaneously, then we can sum up strains in x direction, strains in y direction, and strains in z direction, and see what resultant strain, or should I say net strain, would be developed in each direction when all of these three are simultaneously present, which is what defines a triaxial state of stress. So strain in x direction, if you just sum up these, the strain due to sigma x, strain due to sigma y, and sigma z, you get this sigma x over E minus nu times this. And now we can just, if E is constant for all x, y, and z directions, which is something true for an isotropic element, isotropic material having same properties in all three directions, then you can say 1 over E is a constant, and sigma x minus nu times sigma y minus nu times sigma z. This should be the expression for strain in the resultant strain in the x direction due to all of these three stresses, sigma x, sigma y, and z. Similarly, we can sum up strains in y direction and z direction and reach these results. Hooke's law, this was Hooke's law for normal strains, and Hooke's law for in shear is simple enough, because shear stress in one plane causes shear strain in that plane only. It means when tau xy is acting, it produces only gamma xy and does not produce gamma yz and gamma xz. So they are kind of independent. Now, shear stress alone, when only shear stresses are acting, no normal stresses, then it produces only shearing, only shape changes, and no normal strains are produced. And so shear stress only produces shearing strains, and it means there are no interactions between shearing strain and normal strains. So a normal stress only produces normal strains, and a shear stress only produces shear strains. And then just to mention that the assumption we used was that the material is isotropic, that is, it has same modulus of elasticity in x, y, and z directions, which we have represented by a simple E with no subscript involved. So that's it. Thank you very much.